So this is the question where you can use the superposition principle. And I didn't get to mention this in the first pass review here. This superposition principle, it applies to the electric field and it applies to the voltage as well. You can kind of see it here, this is why the defining equations are useful, because you can use that to infer properties of different objects that are new to you. So voltage, electric potential is a new mathematical object to you, but you know how that's related to other mathematical objects that you're familiar with. And superposition principle applies to the electric field. So, and you know the properties of integral. You know how, if you can express electric field as one part plus another part, you can, you know how you can split it. You can use the distributive property of the dot product, and then you can separate the integral into two separate integrals using, I don't know, associative property of the integral or whatever. And so you can basically separate this into voltage due to one charge distribution and voltage due to another charge distribution. And what that, if you construct that argument fully, not just the hand waving, then what you will have proven is that superposition principle applies to voltage. And that's a useful thing to know. Once you know that, then you can do a question like this very easily. You have electric potential due to one point charge, another point charge, simply add them up, minding where they are placed. So one thing you do have to do is you have to mind what this R means. It means the distance from the charge. So so I won't go through the whole question, but as a quick illustration, if you, so it's describing two positive charges that are symmetrically placed on the x-axis. Let me call this x equals 0. So I have a charge at x equals x naught, another charge at x equals minus x naught. Then you do have to take care in how you write down the expression for the potential. And the fact that the other charge is moving along the y-axis. So let me actually set it up that way so that I'm addressing the actual question, not a hypothetical question, which is not the question. So let's say you are looking at a point here, a point that's described by 0, y. Then as you are applying this formula here, what you have to take care is that R means the distance. So I have to take care that R means this distance here. So I have to be, so if I call this charge Q1 and Q2, as I'm writing down the expression V1, the potential due to charge Q1, I have to make sure this is how I'm writing it. Coulomb constant times the amount of charge divided by R, and this R should be this distance. So it's gonna be square root of, I'm looking at this triangle here, this right triangle. So x naught is one of the legs, x naught squared, plus y is the other leg, y squared. Take the square root to get the hypotenuse, which is my R. So you have to, so when you are writing these expressions for electric potential, you have to mind the setup and you have to correctly interpret what R means for the particular question you have. So with that care, using superposition principle, you should be able to do this question fairly easily. So I won't go through it in full unless there are questions or people stopping me.